Okay, so today we are looking at free energy, delta G. On this page you can see there's a definition known as delta G is known as Gibbs free energy, and it's the maximum amount of useful work available from a spontaneous reaction calculated by taking useful energy from your delta H and subtracting the amount of unuseful energy, entropy. That's all confusing. And why does it smell like cat food in here? Your crackers? Wow, they smell like cat food. Just saying. What was in them?
I don't know, but whenever I eat them, they smell like burning tuna fish.
Okay, I was pretty close. I said cat food. That's pretty close to what burning tuna fish, cat food, pretty much the same thing. So people at home, sorry about the side note. I was just really overwhelmed with this really raunchy smell. God. Man. All right. So we're going to calculate delta G at any temperature because of the T here. Delta G is incredibly temperature dependent. So we have to have that variable available to us if we're not at standard conditions. So the temperature dependence of this will be calculated through the use of the equation that Demo calls ghetto homies. It's ghetto homies take speed. Ghetto homies take speed. If that is upsetting to you and I'm hurting your feelings or anything like that, you can say going home to supper. Ghetto homies, there he is up there above the board. He says I'm bad. Okay, so I actually got a call, email literally 3 days ago. An ex-student said, oh, I'm in an MCAT prep review, a Kaplan MCAT review course, and no one could remember how to find free energy, and I just said, ghetto homies take speed, and everyone thought I was crazy. So, tell you, you'll remember it for years and years and years to come. All right, so this is simple enough to calculate in that your delta G is what we're going to be looking for. Delta H and delta S, since they're not temperature dependent, we can use what to find those? Big Mama from the table. So we're going to use Big Mama to find ghetto homies. And we're not weird. We're not weird at all. Now, one thing though about Big Mama, if you look at your next page, you can apply Big Mama to delta G, but this is only when? At 25 degrees Celsius or 298 K. If you're at 25 degrees Celsius, you can use the tables and find delta G using Big Mama. So just know that that's an option. Now, what else is important about delta G? In the chemistry world, when we talk about free energy, what most people think about is spontaneity. They want to know if a reaction is spontaneous or not by using delta G. Yesterday, you learned a really hard way to find if something was spontaneous. What did we determine yesterday? What of the universe? The entropy of the universe can tell us if something's spontaneous. That's kind of a pain because you have to find delta S of the system, delta S of the surroundings, and add them up. With delta G, you just take delta G of the system, and if it's less than 0, it's spontaneous. If delta G is greater than 0, it's non-spontaneous. We say in the forward direction, but we'll get to that. So kind of the goal of most of the problems with Gibbs free energy is to talk about spontaneity. Okay, so let's just do a little bit of practice with this. I need your calculators out. I need y'all to be fast. Now, I'm actually lying. We're not going to calculate. I'm going to take a look at this table, but this table is really confusing, so I want you to do this to the table. And underneath your chart in your notes, you've got a blank sheet. We're going to make our own table, and it's going to make a lot more sense. And what is this table for? This is answering the question, under what conditions will a reaction be spontaneous? Will a reaction be spontaneous. So all I'm going to do is end up writing ghetto homies 4 different times. And we're going to start out with conditions where, let's say I have a reaction that's exothermic. If a reaction is exothermic, what's delta H? Negative. So I have an exothermic reaction with an increase in entropy. If I have an increase in entropy, what's delta S? Positive. Okay. Under what temperature conditions will I be spontaneous? Keeping in mind that this needs to be negative. Low temperatures? High temperatures? All temperatures. Why all temperatures? And here's the thing a lot of people are missing. You cannot have a negative temperature because we're always in Kelvin. So you're always going to have a positive value. So if I've got a number, negative or not, oh, it is negative here. I have this negative number and I'm subtracting off of the negative number. It doesn't matter how much that is. It's going to stay negative. So this is spontaneous at all temps. So that's our first scenario. All right, let's look at a different scenario. Delta G is equal to delta H minus T delta S. I still want to say exothermic, okay? But I want to have a decrease in entropy, so that's going to be negative. Now what temperature is here? What I'm going to do, watch. I'll use a different color. Positive, positive, right? So what temperatures would this be spontaneous? Nice, low temps. By keeping the temperatures low, this term here won't overtake the negativeness of that delta H, right? All right, let's look at another scenario. Delta G is equal to delta H minus T delta S. Can y'all see behind me? Because I tend to, when I'm writing on the board. All right, now I want to be endothermic, and I want to have an increase in entropy. So that's going to be positive as well. So when is this going to be spontaneous? I want this thing to, it's the only negative I got. I want it to overcome this guy. I heard, what did I hear? High temps, good. Okay, and our last scenario, delta G is equal to delta H minus T delta S. If I'm endothermic, but I have a decrease, that would be negative. Correct, because this plus plus then, never. No temperatures, never. All right, so when do you use this? You were like, so what? When do we use this? Oftentimes on the AP, they'll give you an equation. Let's say they gave you a combustion equation. And they said, at what temps is this equation going to be spontaneous? You don't have numbers, you don't have a table, you might not even have a calculator in that section. What are you going to do? Well, you're going to first look at the states of matter. And in most combustions, you're going usually from a liquid to gases. So if you're going from liquid to gases, what can you tell me about delta S? Positive. What can you tell me about the delta H of all combustion reactions? It's exothermic. Aren't they all exothermic? Okay, so there you go. You know two things. You know that it's exothermic, and you know it's an increase. Boom, you can figure out, oh, this is always going to be spontaneous. So those are the types of questions you might run into, and you have to apply this knowledge. Everything we crossed out on the table said the same thing, but it's done in a really confusing way. All right, let's move on now to actual problem solving. Number 5. The convoluted thing that this silly question is asking, it's wanting us to find delta G 2 separate ways. I don't know if you recognize this, but we had this equation yesterday, and you solved for delta H and delta S in class. But what are the 2 ways we could find delta G? And it says delta G naught, so that's standard conditions. So what 2 ways can we find it? Big Mama. We're going to find it the Big Mama way, and then you're going to find it the ghetto homie way. And if all's well with the world, we should get the same answer. So Big Mama, I don't know if you remember, you had a little table on page 3 of your notes where it gave you delta G's, okay? So So delta G is products, 1 times, on that table it's negative 269 kilojoules per mole. It's 629, negative 629 kilojoules per mole, minus, good news is, the free elements have a 0 free energy, just like delta H does. So all of the reactants, because they're free elements, are 0. So there's our big mama. So our final delta G is negative 629 kilojoules per mole. So that was easy. Okay, so now what I need you to do, go back into the notes. You already found delta H and delta S. You already did Big Mama yesterday. So go back into your notes. I'm going to hit pause on the video, and we're going to record what we found from the previous problems in this packet for delta H and delta S of that reaction. Okay, so we found our delta H and our delta S from our previous problems. I want to take these and plug these into Ghetto Homies, but does anybody see a problem? Different units. We cannot plug these in the same. Since I'm comparing it to a kilojoule per mole, let's just go ahead and have all of them be kilojoules. So this one becomes what? Negative 0.252 kilojoules per mole Kelvin. All right, I'm going to solve for delta G. Plugging in negative 704 kilojoules per mole minus, what's my temperature? 298. I heard some weird numbers being said. I hope you all understand it's 298 minus 0.252. And when you solve, look what you get. Negative 629 kilojoules per mole. What a coincidence. No, it's not a coincidence. It's called state function. State functions are functions or basically values that doesn't matter how you get there. There are multiple ways to get to the same answer. So do y'all remember the flippy thing? Okay, we had multiple equations, and you could flip them for a goal. Because that delta S and delta G are all state functions, we can use the flippy thing for those as well. And I'm not going to go over it because you already know how to do it, but just know if you have a series of reactions and you have a goal equation, you can take them and flip them and do exactly what you did with your delta H's. Okay? We'll practice those in AP problems in the next few days. It's not in the in-class problems, but we're going to practice that. Okay? Questions on this page? All right. Number 6. Pretty important problem. Number 6 says, calculate the temperature at which this reaction occurs spontaneously. Need y'all to brainstorm here. When it says spontaneously in temperature, that's kind of an indicator we have to use Ghetto Homies. But what are we going to put in here? Any ideas? We're solving for temperature because they're asking at what temperature it's spontaneous. When does spontaneity occur? When delta G is negative. So what's the point of delta G becoming negative? 0. So we're going to plug in a 0 for our delta G. And then what? What are we going to plug in for these? Big Mama and solve for table Big Mama. So you're going to find Big Mama. To save us some time, this is what I do with all the classes. I want my first, looks like 2 rows are full. The first 2 rows, I want you guys to solve for delta H. And the last 3, I want you all to solve for delta S. You have the nice, pretty big tables in the back of your notes. So I want you to go ahead and start solving, and I'm going to pause the video. I need for all of you to convert your values to joules. Tomorrow we're doing a reaction where R is involved, 8.31 joules per mole K. Because of that, we're going to need joules more often than not, so everybody convert to joules. Okay, so our rows calculated, and they got a negative 176,000 joules per mole for their delta H, delta S. They got negative 284.8. Those of you at home, please check that you can get those numbers. We're going to set delta G to 0, and you're going to solve for T. So let's go ahead and get that done. We end up with a T being in Kelvin for the answer of 618 Kelvin. Now 618 Kelvin is when it is 0. So if I wanted to say at what temperature range would it be spontaneous, this is a negative and a negative, right? So for this to stay negative, do we need numbers higher than or lower than 618? Lower. So the range is actually less than 618 Kelvin. It's going to be the times for spontaneous. Anything higher than that, it's going to be non-spontaneous. Okay? That's a pretty darn spontaneous. It's hard to get higher than that temperature. All right. We're going to skip number 7 and go to number 8. 7 we'll come back to tomorrow. Okay, this is super ultra sexothermic, like ultimate awesome sexiness of a problem. Yeah, that's that was coined in 3rd period, sexothermic. It's actually endothermic when we're boiling, but whatever. It wasn't weak, it was awesome. So, oh, no? Well, it was either Breck or Gareth. I think it was Garrett. Yeah, but I think Garrett started it. Viraj and Garrett and Breck are like all the same person in that class. Beta 1.0 and 2.0, so. Okay, what's really cool about this is you're going to be able to tell me the boiling point of water, which you know what it's supposed to be, but using thermodynamic values, not taking a thermometer and shoving it in water. You're actually going to calculate it using thermo. Here's the important thing. I first need a reaction describing water boiling. What would a reaction look like when water boils? Liquid. Now, can you tell me about what's in the middle there? When we're on a phase diagram, we're one of those butt diagrams. What was it when we're on the line? What can you tell me about the arrow in between? Not the butt crack, no. What is it to be on the line? I just drew an arrow there. What? Equilibrium. So both of those at the actual boiling point coexist. So in a phase change, we're at equilibrium. This is important because you won't be able to do the problem unless you would apply this. In a phase change, we're at equilibrium. So let me ask you this. If we're at equilibrium, we're going like this, right? My hands, you can't see me at home, but I'm doing this weird thing with my hands. Okay, so that's equilibrium. I'm spontaneous. No, I'm not. 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 What do you think delta G is? 0. Delta G is equal to 0 when you're at a phase change or when you're in a system that's at equilibrium. So that being said, how would you solve for this unknown boiling point? What would you do? It's not much different than what we just did. What would you do? Plug in 0. Use Big Mama for delta H and delta S. I'm going to pause it. Same groups. Do delta H and delta S. Let's get it all in joules. All you have to do is take water gas minus water liquid. It's not a hard calc. You have 44,000, not 440,000. Okay, so we're going to go ahead and solve for temperature. When we do this, we get a temperature of 370. This is Kelvin. Now it's not very meaningful to us. If we were to convert this to Celsius, we'd subtract 273. Give me how many Celsius that is. Okay, but go ahead and round that Celsius to 1/6. 100. When does water boil? 100. That's pretty spectacular. Why is it a little off? Why didn't it just come out perfect? Any ideas? Okay, I can buy that. It's the real world, Landon says. I told you yesterday that you could use the tables for delta H and delta S whenever, right? that they're not temperature dependent? Well, they are, but just minimally temperature dependent. We're pretty far from 25 degrees Celsius here. So the further away we deviate from 25, you know, we're going to start to see some effects on delta S and delta H. So that's why there's such a small difference there. Okay? That was a cough. For those of you at home, that was a cough. Okay, number 9, cross out B. Not necessario. We did some predictions on this yesterday where you all figured out by looking at the states of matter what the predicted delta S value would be, positive or negative. Well, now we're going to go further and we're going to say, well, if we increase the temperature, how does delta G change? Without doing much math, we can figure this out. We already predicted here that delta S is going to be negative because we're going from a solid and liquid to just a solid. So disorder is decreasing. You figured out this delta H earlier. Who remembers what it was? Negative or positive? I think it was like negative 704, wasn't it? So what's going to happen as I increase temperature? This becomes plus plus. What happens to the reaction's spontaneity? It becomes less spontaneous or more positive. Or more positive. Okay. What about this one? I have got no numbers here. Nothing. How am I going to figure this out? I know delta G is equal to delta H minus T delta S. I really only need to truly look at delta S. What's going on with delta S here? We're going from gas, liquid to all gases, so this is positive, right? I don't care if this is negative or positive. It turns out this is going to be positive. Can anyone tell me why it's positive? Look at the reaction. It's the reverse combustion. So all combustions are exothermic. The reverse would be endothermic. But regardless, I don't care if this is positive or negative. We're looking at what's happening to it, and we're subtracting something off of a number. That makes it more and more negative, right? So what is that in terms of spontaneity? More spontaneous or more negative? Okay, almost done. On this next page, number 10, I'm not even going to work these with you because we've done this now 3 or 4 times in the last 10 minutes. But I am going to write down the steps of how to do these problems because I want to make sure you're 100% clear. For each of the reactions listed, find the temperature above or below which the reaction becomes spontaneous. So when you're looking for temperature and spontaneity, you're probably going to have to use ghetto homies. So what is our first step in this problem? We're not going to do it. I'm just going to talk you through the steps. What would the first thing we do here? We're going to set delta G to 0 because we're looking for at the point it becomes spontaneous. What would be the next thing we'd do? Big Mama to find what? To find delta H and delta S. Plug it in, but what's one thing you need to watch for? You got to convert units to be the same. Because on every table, your entropy is in joules per mole Kelvin and your enthalpy is in kilojoules per mole. And now what are we going to do? Solve T. Once we solve T, we can then look at the math and decide whether it's a minus minus or a minus plus or whatever. We're going to have to figure out if it's above or below that T that we're going to maintain the negativeness of the delta G. Okay? All right, so tomorrow we're going to finish up the packet. That's the unit. 3 days. That's it.